the 14.3 notes for statistics honors. In the beginning of chapter 14, we talked about best fit lines, specifically least square regression equations. And these were used in order to predict future values of a response variable or present values. But the one thing that we didn't talk about was how accurate these lines are. Just like when we did any other of the statistical procedures that we had numbers that were dedicated to determining whether how accurate the actual predictions were. So we had confidence levels and things like that. But we need that for regression. We need to know how entirely accurate that regression equation is when it comes to predicting outcomes. So in this section, you learn about a very specific one called the coefficient of determination. This statistical value will determine the accuracy of a regression line in making predictions. But before we get to that, just note that in section 14.3 and 14.4, you basically learn about one statistical measure. Each one of these statistical measures are easily calculated using your TI calculator. So the key is that these sections are dedicated to where that calculation, that value comes from, and how to interpret that value. So just realize that even though some of the formulas that are going on here are going to be a little crazy, similar to the ANOVA section, in reality, the majority of the time you're going to be just using your calculator to find these values. It's important that you know where they come from, which is why you're going to see a lot of the derivation, but also be very, very hooked into how these things are interpreted, what these values mean. Okay, so the first value, the coefficient of determination, is represented by the variable r squared. Okay, it's defined as the proportion of variation in the observed values of the response variable explained by the regression. Well, it sounds very complicated, right? But in general sense, essentially, you're just looking for how accurate the predictions are. That's what r squared shows. Now, the formula for r squared is equal to SSR over SST. So these are values that we compute basically from our data set, similar to what we did in ANOVA, and we're going to do that in 1 second when we go through some examples. Okay, some other important things. The values of r squared lies between 0 and 1. Values near 0 suggest the regression line is not useful in making predictions, while values near 1 suggest it is. Okay, there's no set scale on this type of procedure in terms of interpreting 0 to 1, but generally we sort of determine if it's going to be 0, then it's not useful. If it's 1, it is. So if it's near 1, if it's near 0, we kind of go from there and make that determination. Okay, so you'll see in the formula that we needed SSR and SST, these formulas, so those are actually computed here. There is also one other type of sum of squares, SSE, that we will be using later a little bit, so I'm going to be showing you how to calculate all of them. But the key is once again, you'll be using a table to calculate the first two, and when you get the results, you're going to be plugging it into the formula to find r squared. Again, similar to ANOVA, SST is equal to SSR plus SSE, so technically you only have to calculate 2 of them. So what we're going to do basically is go back to previous examples that we did in chapter 14. Specifically, do you remember this guy? Right? So we had the 3 coordinates, and we plotted them. We actually found our regression line here, right? So we found the proper one, which was y hat equals 1 plus x. We proved that, everything with least squares criterion. We went through and did the whole thing. So what we're going to do is we're going to take that same example and we are going to compute all of the values up here, SST, SSR, SSE, using them so I can explain to you what each one of the formulas actually means. So I'm going to box them. So something sort of new here is that you have y hats in two of the formulas. Remember, y hat is the predicted value you have on the line. Okay, so let's take a look at the table over here. So we have our x and y coordinates, so 1, 3, 2, 1, and 3, 5. Remember that y hat is at that value of x, what is the value of y on the line? What is the predicted? So if I went to 1, what is the value of y on the line? It is at 2. If I went to 2, what is the value of y on the line? It is 3. If I went to 3, what is the value of y on the line? It is 4. So those are our y hats for this setup. And we are going to use them to do our calculations. Well, we also need to know, it looks like all of the variables are in terms of y this time around. So we're going to need y bar. So y bar is the average of this column here. So that is, the numbers are 1, 3, and 5. So the average of that is 3. So I'm going to, wherever I see an initial y bar, I'm going to put a 3 in there. So that's what we're going to do as we go through. So I'm going to see if you can follow the best you can. This is the only time we're going to do this live. The rest of it I'm just going to fill in for you because it's a lot of work and we don't do a lot of computation of r squared from scratch. So if for the first column right here, we need to take every value of y and we need to subtract 3. If we do that, we're going to get 3 minus 3 is 0, 1 minus 3 is negative 2, 5 minus 3 is 2. All right, so now, now what do we have to do? We have to take that column and we have to square it. So we're going to get 0, 4, and 4. Okay, so if you look at the formula up here, SST, this total sum of squares, is equal to the sum of that column. So that's going to be equal to 8, which means we already know the denominator of r squared, which is over here. Okay, moving on. So now we need to take every value of y hat and subtract 3. So we're going to do 2 minus 3, which is negative 1. We're going to do 3 minus 3, which is 0. And we're going to do 4 minus 3, which is 1. So we're going to have those values. All right, so what is this column? This is squaring the previous column and getting 1, 0, 1. So if you look back at our formula for SSR, this is the sum of that column, which is what we get as 2. We therefore know the numerator of this is 2. Now that we know SST and SSR, 8 and 2, we know that SSE is going to be 6. But and note we don't need it for the calculation, but I want to show it just because it does come up again in future sections, so I want to show the calculation. So let's just show how you would do that from scratch. So this column here, y minus y hat, is taking every one of your y's and subtracting your y hat. So it's going to be, the first one is 3 minus 2 is 1, the next one, 1 minus 3 is negative 2, and then 5 minus 4 is 1. The next column is squaring each of those, 1, 4, 1, and clearly if you add them up, you are going to get the 6 that we talked about. So this is how, if you're asked to do this in the future, if you're asked to find each one of these values, then that is what you're going to do. You're going to use this little chart in order to figure out what SST, SSR, and SSE are, and those will be the values. So let's go to r squared. So r squared looks like it's going to be 1/4, which is 0.25. So our value of r squared is 0.25. So remember, the scale is from 0 to 1, right, of r squared. So 0.25 is a little bit closer to 0-ish than 1. So that means not so good things for our regression line. So what would we say in technical terms? We would say right here, we therefore state that 25%, right, 0.25, 25% of the variation in the observed y values is explained by the regression. That is the formal statement for r squared, which you want to know. And then you interpret r squared by what it means. It says this low value of r squared would insinuate that the regression equation would not be a good predictor for this data set. So yes, so believe it or not, we went through all of that work in chapter 14 at the beginning, 14, 1, and 2, to show that this was the least squares regression line. It was the least sum of squares error, but it turns out that this would be a very poor predictor for these 3 points in this data set. This shouldn't be too surprising. This often happens when there's very few data points, usually in these scenarios. But it turns out that even though this is the best least squares regression line, it is not a great predictor for these set of points that are here. Well, moving on, let's look at one more example using the calculation, just so you get it again. We are not going to do the calculations out. I am just showing you them so that you get a good idea what it is, but I am going to talk you through the process. So remember, we had this car and price example where we actually superimposed this line here, right, on top of the data points for the age of a car versus the price in hundreds of dollars. So we ended up with this regression equation in the meantime. So what if you were asked to calculate R squared from scratch, which means, again, you would have to calculate SST and SSR. Well, SST is computed by, again, remember, y minus y bar, which is right here, squared, the sum of them. So what I did was I brought in the age and the price here, right? If you return to the previous examples way back when, our R bar was calculated to be 86.64. You can actually calculate that by doing 975 divided by the 11 observations if you'd like, but that was the value we got in the previous section. So what do? Essentially, this column will take every value of y and subtract 86.64. So for example, 85 minus 86.64 is negative 3.64. I did all the work for you, and you would end up with all of these values calculated for y minus y bar. And of course, this column is all of those values squared. So again, if we took negative 3.64 and squared it, we would get 13.2. We would do the same for all of them and end up with all of these values. So remember, SST is the sum of all of these values, which would be down here. So if you add up all these values, you get 9708.5, which means that our SST is 9708.5. So in this scenario, this would be the numerator or the denominator of our R squared calculation. So I did the same thing for SSR. So what do we basically have to do? So let's say we do have all of these values. So remember, I'm going to bring down y hat, see if I can remember it here. So 195.47. So y at 195.47. And we're subtracting 20.26x. Okay, so this is our y hat. So we have our xy's right here. So what is y hat? Y hat will be taking every single one of your x's and plugging it into the regression equation. So if I put 5 into this equation right here, 20.26 times 5, and then subtract 195.47, I am going to get 94.16 as my result. So same thing if I take 4 and I plug it into the equation, I am going to get 114.42 as my result. So I would do that for all of them. I would take all these numbers and plug them in, and you could see wherever you have repetitions, you have the repetition in y hat because you're plugging in the same number when you're doing so, if that makes any sense. So that's where all these values come from, right? So we get our y hats. So this column is taking all of our y hats and subtracting our y bars. So remember, y bar is again 86.64. Okay, so we're going to take 94.16 and subtract 86.64 and get 5.53. We're going to take 114.42 and subtract 86.64 and get 25.79. You're going to do the same thing for all of these. Again, you're going to get repeated values because you're subtracting the same numbers, and you're going to get all the y hats minus the y bars. Last thing to do is you square every value over here. So square 5.53, get 30.5. Square 25.79, get a very large 665. Do the same thing for all of these, and then take the sum, and you are going to get 8285. Okay, so if we have those two values, note we do not need to find SSE yet. We will just as an exercise, but for now, we now have the two values of importance. We have SSR, which is 8285. We have SST, which is 9708.5. Which is going to give you approximately 0.853. Okay, this is our value of R squared, so we would say 85.3% of the variation in the Y values is explained by the regression. That is the formal statement of R squared, but generally, to interpret that, we would say this higher value of R squared would insinuate that this regression equation would be a good predictor for this data set. So what does that mean? That means that this regression equation is actually quite effective in predicting all points on this line. So if we just took like 3 and we wanted to predict its value, then we would be pretty confident that whatever value we got would end up being the price of that car for that age. So that's the idea when it comes to R squared, where it comes from and how to calculate it. Okay, so again, just to be clear, SSE does not need it in order to calculate R squared, but because we probably will be using it in future lessons, I wanted to make sure to bring it up. So if you needed to calculate SSE from scratch, let's say, and even maybe you'd have to do it in the homework, I don't know, I don't remember, but if you were to do that, what I did was I did the calculations over here. So just remember a y hat comes from the regression line, right? So it's the same numbers that are here, same numbers. So instead of subtracting y hat minus y bar, instead we're doing something much easier. We're literally just taking these two columns and subtracting them. So 85 minus 94.16, negative 9.16. 103 minus 114.42, negative 11.42. Then this column squares all those the values. So negative 9.16 squared is 83.9. And then the sum of them will be 1,423.5, which is your SSE. You can very easily verify that by just taking 9708.5 minus 8285. So 9708.5 should be equal to our SSR, which is 8285, plus our SSE. Okay, so I believe this works out. I didn't check it, but I think it works out. So you'll end up with that as your result. So just in case we have to do that later on, that is how you do the computation for that. Okay, so the last thing in this section is the calculator. Right? So how do you calculate R squared in the calculator? Right? So believe it or not, it is in the same command as linreg. Right? So let me just look real quick so I get this all set up for you. So if you go to stat calculate and go to, again, number 8, which is, actually, let's put it over here. If you go to linreg for number 8, which is the a plus bx one, if you did that prior, you probably only saw the regression line with a and b under it. Believe it or not, there are also 2 other variables that should be under there, but it needs to be opened on the calculator. So how do you do that? So if you go to the number 0 on the calculator, above it, you're going to see a word called catalog. So what you're going to do is you're going to hit the second key and you're going to hit 0 so that you get catalog. Okay, when you go to catalog, it's basically a list of every command in the entire calculator. So what you need to do is you need to hit the down button until you get to the command diagnostics. So let me just go down there to make sure I have it perfect. So you go down until you get the diagnostics on. So we get, or there we go. I want to make sure diagnostic on. Okay, so you hit the down button, and the down button, by the way, is a part of the cursor key. So basically you're hitting this thing, whatever, the down button. and you're going to diagnostics on, you're going to press enter and then press enter again. So you click on it itself, you click on it again, and then you should see diagnostics on and then done on the right side. Once you have that, go back and do linreg again, and these two values should show up. The one that you want right now is r squared. So for example, I believe right now you have this entire data set in your calculator because we just did it in the beginning of chapter 14. So what I want you to do is go to linreg again, do L1, L2, and then hit the button, and these what should show up is r squared, and you should see 0.853-ish as the value. So I want you to verify that just to make sure all is good. From now on, when you're asked for the value of r squared, if they aren't looking for anything in the derivation, that is all you have to do is use the calculator command to get it.